Hi children, today's first topic is non-polar and polar dielectrics. What are non-polar and polar dielectrics? As you all know, that what is a dielectric? Dielectrics are the insulating materials which transmit electrical effects without conducting. Okay, without conducting, they can only transmit the electrical effects, right? Okay. Now these dielectrics are divided into two. One is non-polar dielectric and polar dielectric. First we'll see what is non-polar dielectrics. See, if you see in every atom, okay, positively charged, what is that, proton inside the nucleus and the negatively charged electron cloud surrounding it. Okay, now there exists what is that, center of mass. If you see the center of mass of all the positive charge, all the positively charged protons, and the center of mass of all the negatively charged electrons. Okay, see, that actually plays a very important role here to differentiate polar and non-polar dielectrics. See, in the case of non-polar dielectrics, actually what is happening here, if you take non-polar dielectrics, that is molecules, okay, there the center of mass of all the positive charge, okay, and the center of mass of all the negative charge, the positive charge proton, and the center of mass of all the negatively charged electron, okay, both of them, they coincide with each other. Okay, the center of mass of the positive and the negative charges, positive charge protons and negative charge, what is that, electrons, both they coincide with each other. Okay, you know very well, equal number of positive charge and equal number of negative charge. Therefore, in an atom, therefore, if they coincide with each other, what do you say about the dipole moment? What is the dipole moment? Because positive, equal number of positive and negative charges there, but they are not separated. They are embedded. They are actually both are coinciding. Therefore, 2a that is equal to 0. You know dipole moment P that is equal to Q into 2a. 2a is equal to 0. Therefore, dipole moment that is equal to 0. Correct? Therefore, here in the case of non-polar dielectrics, okay, therefore the center of mass of positive charge coincides with the center of mass of the negative charge in the molecule. Okay, therefore each molecule has a zero dipole moment in its normal state. It doesn't have any dipole moment of their own. Okay, so at normal state, okay, without any influence, its dipole moment of each and every molecule of non-polar dielectric is equal to 0. Okay, that gives such molecules are highly symmetric in shape, Example, you can say non-polar dielectric: hydrogen, okay, nitrogen, oxygen, carbon dioxide. Okay, therefore these are all see, hydrogen, nitrogen, okay, and you can say benzene, carbon dioxide, methane, etc. They have, what is that, a very symmetric shape. Okay, why? Because they belong to non-polar dielectric. Their center of mass of positive and the negative charge, they coincide with each other. Okay, right. Now then we'll go to polar dielectrics. Then just what are polar dielectrics? Polar dielectrics are, okay, where the molecules are such that the center of mass of the positive charge and the center of mass of all the negative charges, actually all the protons, the center of mass of all the protons is positive, center of mass of all the electrons, negatively charged electrons, it is negative, right? Therefore, they are separated by some distance. Okay, they are separated by some distance. Therefore, here, see, such a molecule where the center of mass of the positive and the negative charges, okay, they do not coincide with each other. Here, the non-polar dielectrics, they coincide, but here they do not coincide with each other. So, they have non-zero dipole moment. Therefore, P is not equal to 0 here. Dipole moment is each and every molecule has its own dipole moment at normal state, no influence. As such, it has some dipole moment. Every molecule is having some dipole moment of its own. Therefore, that gives. Okay, therefore, because of this, it gives some, what is that? Some asymmetric shape. These polar dielectrics, usually they have some asymmetric shape. Okay, therefore, example for that. Example, if you say, I can say water. Okay, water, alcohol, you can alcohol, ammonia, okay, and HCl, etc., etc. They, if you see, they are, what is it, polar molecules. They are polar molecules. Okay, even without any external, at normal conditions, I am telling, in normal conditions, okay, it has its own dipole moment. Then it is what is called polar dielectrics. Is it clear? Right. Now with this, if you know this, what is polar and what is non-polar dielectric, then with this we'll go to the next topic. Okay, what is it? See, it is what is called a dielectric polarization. Now next topic is dielectric polarization. What is it? See, very what is it? It's very important concept. See, if you take a non-polar dielectric, as I told you, see, non-polar, in non-polar dielectric, okay, see, you know that at normal state, you know that, see, center of mass of positive and the negative charge, it coincides here, coincides with each other, right? Okay, normal state, what is that? There is no external, what is that, influence. There is no, it is not kept in any external field. Okay, therefore external field, if you say E naught, okay, that E naught, that is equal to 0. In the absence of any field, in its normal state, it doesn't have any dipole moment of its own. Why? Because center of mass of all, both positive and negative charge, they coincide with each other, right? But when a non-polar molecule, just I have taken only one molecule, after that I will take a dielectric, okay? I have taken one single molecule. If I take, if a non-polar molecule is kept in an external field, okay, external field, what is the direction of the external field here? It is in this direction. Okay, therefore, now when it is kept like this in an external electric field, it is an external electric field. Okay, what happens? E naught is in this direction, means this side will be, electric field lines will go from positive to negative, correct? Electric field E naught will be from positive to negative. Okay, therefore, now what happens? When a non-polar dielectric is kept in an external electric field, now see, the center of mass of positive and negative charges, okay, will have some disturbance. What is a disturbance? You see, the negative charges will be pulled towards the left. Why left? Here positive is there because it goes from positive to negative electric field. And all the positive charges will be, what is that, attracted, that will be pulled towards the right side. Okay, therefore what happens in the presence of electric field? Okay, therefore what is happening here is, here is negative charge. Center of mass of the negative charge will be shifted to the left side and center of mass of the positive charge will be shifted to the right side. Are you following? Why? Because of the external electric field. As such, if there is no electric field, both the center of mass coincides. But when it is kept in electric field, you know electric field is from positive to negative. The center of mass definitely will be attracted. So now what happens? See, electric field is pulling the center of mass of positive and negative charge apart. At the same time, there will be some attraction between force of attraction between the positive and the negative charges. Both will be there now. So there are two forces. One is force due to external field, and the force, another one is force due to for attractive force due to the positive and the negative charge, center of mass of positive and negative charge. But at one point, what happens? There is a balance. They reach a balance. Okay, and or at they are, which means that they will come to an equilibrium. Okay, they'll come to an equilibrium position. That time what happens, this okay, therefore what happens till then, at that instant you can say that all the there is a positive and the center of mass of positive negative charges slightly it is separated, and it is said to be, the molecule is said to be polarized. Now molecule is polarized now when in this case. Okay, therefore this is how non-polar dielectric molecules, now once it is polarized, what do you say here? Here there is, it has some induced dipole moment. Previously there is no dipole moment, P is equal to 0 na, isme dipole moment. Okay, but here P is not equal to 0 because there is a non-zero dipole moment. This dipole moment is what is called induced dipole moment. It is not its own dipole moment, but in the presence of electric field. Once electric field is switched off, immediately the center of mass, both the center of mass will coincide with each other. As long as electric field is present, there will be, what is that? A dipole moment. Hope you are following. Okay, therefore this is about non-polar, that is a molecule. Okay, single molecule I have taken. If a block of non-polar dielectric is taken, for example, see, if I have a block, see here, I have a block of this one. I have, okay, plus or minus, okay, plus or minus, okay. What do you mean by that? Plus or minus means what is it? It is a coincidence of center of mass of positive and negative charges, like that. Here I have taken only one molecule. Here I have taken one block of non-polar dielectric. Okay, this is equal to E naught is equal to 0. When I am keeping is this same dielectric in a electric field, therefore E naught here. What is E naught? E naught will be in this direction. Okay, in that case what will happen? Okay, all the negative charges by every molecule, what is a negative and positive separation ho jayega na isme, like that. Here negative positive negative positive negative positive. Why? It is because of the presence of what? The external field. Are you following? Okay, therefore, see, it is nothing but what is that here? It is E is present. In the presence of E, there is an induced dipole moment is there. It is with respect to single molecule. It is with respect to non-polar dielectric slab. Okay, when it is kept in an electric field, it will be. Right. Now, in the case of polar dielectric, see, polar dielectrics, already they have dipole moment now. So, what will happen when it is kept in electric field? We'll see. Therefore, polar dielectrics. When in the case of polar dielectrics, what actually is happening here? See, already they have some dipole moment of their own, because what is that? Here you come this side, see your positive center of mass of positive and negative charges. Okay, they are actually not coinciding. There is some distance of separation. Therefore, P is actually not equal to 0. They have some non-zero dipole moment of their own already. But what is the difference here? What is the problem here? See, these at a normal condition. That is, I am not applying any electric field. Let me take a non-polar. Let me have use some other color so that to differentiate. What color is there? Okay, right. Let me see how it works. Okay, therefore this is okay, fine. This is the, what is that, polar dielectric. Okay, polar dielectric when E naught that is equal to 0. First, as I told you, every molecule, it is having its own dipole moment now. Okay, but what is here, there is every molecule is having what is that, dipole moment of their own, but they are randomly oriented. They are randomly oriented. What do you mean by random orientation? Random orientation. Why random orientation? Because of thermal agitation. See, external thermal energy na? Outside the what is that, dielectric, what is that, there is some thermal energy is there. The molecules, they absorb the thermal energy, and because of that, they, what is that, there is some randomness is there, thermal agitation. What do you mean by this? See, though they have non-zero what is the dipole moment, minus plus non-zero only na? Okay, this is one molecule, center of mass of positive and negative. Okay, and here like that, it is not in the same direction. Here dipole will be, dipole moment is from left to right, here it will be in this direction, correct? Therefore they are randomly oriented. Why? Because of thermal agitation, they absorb thermal energy. Because of thermal agitation, what happens? Okay, the dipole moment, they have non-zero dipole moment, unlike your, what is that, the non-polar dielectric. Here in the case of non-polar dielectric, in the absence of electric field, okay, center of mass of positive and negative charge, they coincide, but here they are not coinciding. Every molecule is having a non-zero dipole moment. Hope you are following. Like this. Okay, but okay, why it is always, see it, if it is plus, here this will be minus. Okay, like that, randomness, there is a randomness is there now. Okay, random, because of that, what happens here is different direction, they are randomly oriented, dipole moments are randomly oriented. Therefore, what is the net dipole moment of this dielectric? Net dipole moment, what is net dipole moment of this full slab, if you take, because of the randomness, or it is also called dipole moment density. Net dipole moment, okay, that is all dipole moment density, whatever you want. Net dipole moment of the full slab, that is nothing but equal to 0. I hope you are following the difference. See, if every molecule is having a dipole moment, no doubt, but they are randomly oriented. If you take a slab as such, okay, the polar dielectric, all are randomly oriented. Because they are randomly oriented, what is that, net dipole moment, that is equal to 0. Because of the randomness. Why this randomness? Because of thermal agitation. They absorb energy, thermal energy from outside, from the surrounding, and because of that, what is that, the randomness will increase. Okay, as the temperature, outside temperature increases, the randomness will also increase. Are you following? Therefore this, that is why the net dipole moment equal to 0. Okay, now what I am doing, I am applying the electric field. If I apply the electric field, what will happen? Now we are going to see. See, now I am applying an electric field. In which direction? In this direction. Now you know very well what will happen. There is what is that? Because of that, all the center of mass of the negative charge will be pulled to the left, and the positive charge will be pulled towards the right. Okay, as we have seen in the previous non-polar dielectrics, right? Therefore, what will happen? Okay, if the external electric field, that is very important, the randomness will decrease. Definitely. In the absence of electric field, randomness is more. But in the presence of electric field, randomness definitely it will decrease. Okay, and if the external electric field is very strong, okay, because the randomness is because of thermal agitation, but your external electric field tends to, what is that, align. What is it, dipole moment direction here? Don't know what is the dipole moment direction. P, that is also from negative to positive. No, P is also like that. The external electric field, okay, it actually tends to give, what is that, orient all the dipoles in a particular direction, in the direction of the electric field. Okay, it will try in the direction of the electric field. But because of thermal agitation, what is that? That it will just oppose that orientation, oppose what is the electric field. At one point, the electric field is strong enough. If it is strong enough, then what happens? Okay, you can overcome the thermal agitation. Therefore, every molecule can overcome the thermal agitation because of that. If you are applying a strong electric field, okay, so that what happens? There will be, now it has become like this, L the molecule. Are you following? Okay, because in the presence of what is that, strong external electric field, okay, now the thermal agitation molecule is able to overcome thermal agitation. Therefore, all the here dipole moment will be in this direction. But here dipole moment are randomly oriented. Here dipole moment is in the direction of the electric field itself, because electric. Are you following? Okay, therefore, that is the difference between polar and non-polar dielectrics. Non-polar dielectric doesn't have the P, that is a dipole moment, in the absence of electric field. But polar, they have, but they are randomly oriented. Therefore, dipole moment, net dipole moment will be 0 because of the randomness. Okay, but once you are applying the electric field, strong electric field, then what is that? There will be, all the dipoles will align in the direction of the electric field, hence you will be getting a net dipole moment. Okay, in this case, net dipole moment here is non-zero. Okay, P here is not equal to, not P here also, P is not equal to 0. Every molecule is having here dipole moment or net dipole. Net dipole moment, okay, is not equal to 0. Are you following? Which means there is some net dipole moment because of the application of strong electric field. Hope you are following. Right. With this, we will go to the next topic. Yes. See here. Now it is a continuation of the topic. Now what I want to do is, see, I have. Let it be colorful. I'm using all the colors. Just okay. See, if what I want to do here is, I'm going to see, if you take with respect to non-polar dielectric, I think polar and non-polar you have idea. Now let me have, see, if in the case of non-polar dielectric, in the case of okay, dielectrics. Now I have a single molecule. I have what is that? One single non-polar molecule. Okay, and in the presence of an external field, it becomes, I think, a non-polar molecule here, na. And in the presence of electric field, it acquires some dipole moment. Okay, dipole moment. And what is the direction? Dipole moment in the direction of the electric field. Electric field is from left to right. Dipole moment is also from left to right, na, negative to positive, right? Therefore, this dipole moment is what is called induced dipole moment. Therefore, in the case of non-polar dielectrics, induced dipole moment. Why induced dipole moment? In the absence of electric field, no dipole moment. But in the presence, it is having. Okay. Therefore, the induced dipole moment, okay, is actually directly proportional to magnitude of the induced dipole moment is directly proportional to external electric field. Okay. Therefore, you can say P, that is equivalent to some constant here. The constant here is, see, alpha epsilon naught A naught. Okay, epsilon naught, you know very well. what is that? Absolute electric permittivity. Okay, and what is alpha here? Alpha is a very important constant of proportionality. Alpha here is what is called atomic or molecular polarizability. Polarizability. Okay, atomic or molecular polarizability. I think this is some dielectrics. There is some. Okay. Atomic or molecular polarizability. Okay. Therefore, what is, if you see, what is alpha here? Alpha, that is equal to P by epsilon naught E naught. Okay. So, if you substitute the unit, what is, I just want to find out what is the unit of it. Is what is P? P is nothing but Q into 2A, therefore coulomb meter divided by epsilon naught. Epsilon naught is coulomb squared per Newton per meter squared. Okay, the already I have written the test also in this topic. Okay, therefore it is Newton per coulomb. E naught. Therefore, if you see this, it will be meter cube. Meter cube. Alpha, unit of alpha, okay, is meter cube, which means that it has a unit of volume. It has a unit of volume. And what is the value of alpha? Alpha values, it is ranging from 10 power minus 29 to 10 power minus 30 meter cube, which is also of the order of atomic volume. Atomic volume range is this one. Okay, right. So this is about when I am keeping a single molecule, okay, in a electric field. Which molecule? Non-polar molecule. If I keep a single non-polar molecule in electric field, you know very well it is what is that? Polarized. It is it acquires some induced dipole moment, and the induced dipole moment of the non-polar dielectric is directly proportional to E naught, and this we have seen. Right. Now I am going to have the next very important term. Here it is single molecule. What I am going to do is, if I keep, okay, now I am going to keep a non-polar dielectric slab, non-polar dielectric slab in a external electric field. Okay, therefore, see, I am going to keep let me draw a big diagram so that, because something I have to show so many things inside. So it is uniform electric field. You know very well what is that? The method to produce, this is positive and this is negative. Therefore, it is an external electric field. What is the direction of the external electric field? E naught. Okay, it is from positive to negative, right? Okay, and now I am inserting a non-polar dielectric here. Okay, let me have a non-polar dielectric. I am inserting here. It is a slab, non-polar dielectric slab. Okay, I am inserting here. Okay, right. So when I am inserting a non-polar dielectric, it is a pink color. Huh? Okay, you want pink color then? Okay. Okay. Now this is E naught. So now I am inserting a non-polar dielectrics, because after here let me have a non-polar dielectric here, and I'm going to name it ABCD. It is kept inside. Okay. Now let it be A, B, C, D, whatever is it. Okay. Now, when I'm keeping it inside, okay, therefore all the atoms here, therefore the electric field is E naught. E naught, it is an external electric field, it's outside. Now, each and every molecule or atom inside, whatever, okay, therefore that will get uniformly, it will be getting polarized. Okay, therefore how it will look like, see here, you can say negative, positive, okay, negative, positive, negative, positive, like that, like that. Let me have a gap here, because it is not that this much gap won't be there, just okay, like that. So many, all are, they are, it is nothing but non-polar dielectrics, okay. But once I am keeping inside the electric field, now you know very well, center of mass of all the positive and negative charges will what is that, be pulled. Okay, therefore there will be induced dipole moment. Okay, therefore if you take this is a single molecule, one molecule. Okay, therefore if you take a single molecule, okay, and what is the distance of separation between, if you take here, I have taken a negative, positive, and a single molecule I have taken. What is the distance of separation between the center of mass of positive and negative charge here? If you take here, this I am showing here, okay, it is x, let it be x. Okay, and the charge center of how many charges are there in each atom, then it will be q, minus q, and here it is plus q. Okay, therefore it is it acquires some induced dipole moment, because it is after all non-polar dielectrics. When it is kept in electric field, what will happen? It acquires a dipole induced. Therefore here induced dipole moment, okay, of each molecule here. Okay, that is nothing but P. Okay, that is nothing but Q into X. Q into X. Why Q into X? Q is the charge and X is the distance of separation. So every molecule now, it has some induced dipole moment. Very good. Okay, therefore, now what I want is, if there are, if there are n number of atoms, okay, per unit volume, okay, in this ABCD, per unit volume of ABCD. Okay, therefore can you give me what is a dipole moment? Therefore, what is a dipole moment per unit volume? Okay, every molecule is having a dipole moment, Qx. Now, how many number of atoms per unit volume? N number of atoms. Therefore, what is the dipole moment per unit volume? Dipole moment per unit volume is denoted by capital P. Small p is a dipole moment of a single molecule. Capital P means dipole moment per unit volume, and that is nothing but for every, how many, what is the dipole moment of each atom? Qx. Okay, how many number of atoms are there per unit volume? N. Therefore you can say, okay, Qx into N, that gives you dipole moment per unit volume. Are you following? Therefore, what do you about this is nothing but, okay, dipole moment density, dipole moment per unit volume. Therefore, P is also called as dipole moment per unit volume, or P, okay, is also named as dipole moment density. Dipole moment density, or the other name, let's see, dipole moment per unit volume, P is called as, what is that? Dipole moment density, Also, there is one more name. It is electric polarization. Electric polarization. Polarizability, yes or Z, whatever is that. Okay, right. Are you following? P is dipole moment per unit volume or dipole moment density, or it is also called dipole. It is also called what is that? Electric polarization. Okay, what actually it means? It measures the extent of polarization of the dielectric. Extent of polarization. If a non-polar dielectric is kept in an external field, okay, to what extent it can be polarized? That is given by, okay, that is given by, what is that? P. P measures that. Okay, therefore, what is a unit? SI unit of P. What is SI unit of P? You tell me. It is nothing but coulomb meter, because it is P into X, na? That is nothing but P, small p into N. Correct? Small p, qx is small p, na? This is a dipole moment. Here it is number of molecules per unit volume. Therefore, dipole moment per unit volume. Correct? Dipole moment. This is into what is that? N. N is not. What is the unit for N? What number of molecules per unit volume, per unit volume, it is not just number of atoms per unit volume. Therefore you can say per meter cube. Okay, therefore you can say that is nothing but coulomb per meter squared. Coulomb per meter squared, it is nothing but surface charge density, no? Therefore it is sigma. So you can say that, okay, P can also be named, what is it? Is surface charge density here in this case. Are you following? Are you following? Okay, so this is about what is that? P, right? That is which P? Capital P. Small p means dipole moment of individual molecule, and capital P means dipole moment density. Okay, okay. Now next one. Now let me go to this one. See, that for each now what happens if I keep a dipole ABCD inside the electric field? Actually, what is happening? See, all are packed, all the molecules are very very close. It is, I have drawn as highly separated here. Why? Because just to make you understand, because it is a gap I have deliberately have left. It is not like that. That be fully packed. Okay, so here what happens? This is one atom and this is the other atom. Okay, and both are very close. Once they are very close, what will happen? This positive and this negative are very close, na? This positive, this negative, this positive, this negative. Are you following? Okay, they are very close, na? Okay, this positive, this negative, this is positive. So positive and negative center of mass of nearby atoms are very close. Therefore, they cancel each other. Therefore, they cancel each other. Therefore, what will be? So, because they are cancelling each other, the same thing, how it will look now. See, this is the external field. Okay, this is a problem. This is the external field. Okay, and positive, negative, it is E naught in this direction, and inside you are keeping a which one? A dielectric slab. Okay, which dielectric slab? Non-polar dielectric slab. Okay, the same thing. What will happen now? I told you something. What is that? The nearby center of mass of positive and negative, positive charge of one atom, and the center of mass of negative charges, the nearby atom, they cancel because they are very very close. Okay, therefore now what is happening? Okay, now what will happen? Because they cancel, so it will be left only with the surface charges, only on the surface, because it doesn't have anything to get cancelled. The extreme end charges are there now. Left side extreme end, these charges. Okay, and right side extreme end positive charge. Are you following? So that will be left. All the other charges inside everything will cancel. Are you following? Therefore, now one left side extreme end is negative and right the slab. Well, now what is the A B C D now? So in A B everything is what is a negative and C D it is positive. Okay, therefore now you tell me inside the dielectric there will be one more electric field now. Okay, is may positive, therefore that will be from positive to negative. Are you following? And this is because of polarization. Electric field due to polarization. Are you following? So it is EP. That is why it is what is that? This electric field. Okay. Therefore, that is induced charges are at the extreme ends. That is negatives the at AB and all the positive charges at the CD. In between, all cancel. Therefore, that by producing what is that? An electric field. This electric field is due to because of that polarization. Okay. Therefore, yeah, that gives that is where the direction will be just from right to left. It is opposite to E naught. Okay, therefore EP and E naught are in opposite direction. Therefore now, are you following? Therefore the effective electric field, okay, in the now the dielectric is polarized now in the polarized electric field, polarized dielectric inside. Okay, inside the polarized dielectric is nothing but given by E. Okay, what is that E? E is nothing but E naught minus EP. Why minus? Both are in opposite direction. It is a value. Okay, E naught, that's a magnitude. E, that is nothing but E naught minus EP. What is E? E is effective electric field, and all other name here is E is also called as E is also called as the reduced value of the electric field. Reduced. Why? Reduced value of the electric field. Okay, inside the dielectric. Are you following? Because of polarization, there will be an induced electric field. The electric field is because of the induced charges. Therefore, that is electric field. It is what is due to polarization. Okay, are you following? Okay, therefore that will be from right to left. Therefore, you will be getting the reduced value of the electric field as E is equal to E naught minus EP. Are you following? Now, very important now. What is EP therefore? Now I want to find out what is EP. Therefore, see here what are all the charges here. Here this side because of this polarization, here it is minus Q charge and here it is plus Q charge. On AB, how many charges are? Minus Q number of charges, and in CD plus Q number of charges are there. Okay, therefore, and what is the surface charge density? Let the surface charge density be sigma. Okay, therefore I can write EP in terms of surface charge density for sigma by sigma by what is that? It is not epsilon naught. Why? Because it is inside the dielectric. Therefore it is not epsilon naught, but it is epsilon. What is epsilon? It is absolute permittivity of the dielectric. Absolute permittivity of the dielectric. Are you following? Therefore that is nothing but, okay, 1 by epsilon into Q by A. Q is the charge on the what is that surface on AB and CD on both the side. Okay, and let A be the area of the plate, area of this. Okay, therefore you will be telling Q divided by A, and that is Q by A. You can say that sigma na, that you can write even P by epsilon na. What is P? Just now we have seen here P. What is P? P that is equal to, okay, sigma P, that is equal to surface charge, because coulomb per meter squared. Therefore, I told you it is sigma. Therefore, P is nothing but dipole moment density. So, you can say that sigma by epsilon can also be written as P by epsilon, where P is nothing but electric polarization or dipole moment density, total dipole moment density. Are you following? Right. Now, very important one. See, it is found that the ratio between, in the case of what is the dielectric polarization, E naught by E now, what is E naught? E naught is applied field. What is E? Reduced value of the electric field in the dielectric. Okay, that gives you automatically the dielectric constant of the slab. Okay, therefore, see, E naught, what is the E naught by E? It is therefore, what is E here? Here, what is the net field inside E? That is equal to E naught minus EP. E naught minus EP. Correct? And are you following? And your field E naught will be very strong, definitely. Therefore, your net field will be from in the direction of E naught, applied field. Okay, right. Therefore, the ratio between, so your ratio of the external electric field, okay, applied electric field, okay, and the reduced value of the electric field, okay, is a constant, and the constant is what is called, that gives you the dielectric constant of the material. It is nothing but the dielectric constant of the material of the slab. Of the material of the slab. Are you following? Is it clear? Now with this, let us go to the next. Now what is that? Now one more term I am going to introduce now. E naught by E is equal to K is fine. Now I am going to introduce one more term, what is called electric susceptibility. What is electric susceptibility? It is seen that, see, the electric polarization, or it is dipole moment density. Electric polarization, or it is what is called dipole moment density. That is, don't write P, na? Okay, P is directly proportional to the reduced value of the electric field. Directly proportional to the reduced value of the electric field. What is this one? It is dipole moment density is directly proportional to the reduced value of the electric field. I think, can you recall the previous one? In the case of a single molecule, okay, induced dipole moment of, what is that? Single molecule. I have taken only single molecule here. Okay, here it is the dipole moment of a single molecule directly proportional to the external field. Therefore, P is equal to alpha epsilon naught E naught. Therefore, but here it is completely different. Here, dipole moment density. It is not a single dipole moment of a single molecule, but it is a dipole moment density of the nonpolar dielectric when it is kept in an external field E naught. Is directly proportional to the reduced value of the electric field. Okay, therefore you can say P, that is equal to some constant of proportionality here, epsilon chi. It is what is called chi E, epsilon chi E. Okay, now what is epsilon? Epsilon, you know, it is nothing but absolute permittivity of the medium, that is dielectric. Okay, and chi is what is called, okay, electric susceptibility. Of the medium. Electric susceptibility of the medium. Okay, therefore what is electric susceptibility? Yes, electric susceptibility, okay, of the medium means what is a dielectric medium, that is nothing but dielectric. Okay, so here the electric susceptibility describes What the electrical behavior of the dielectric? You know, dielectric, okay, it transmits electrical effects without conducting. Therefore, that electrical behavior of the dielectric, okay, is described by chi, that is measured by chi. Are you following? And the value of chi is different for different dielectric. Value of chi is different for different dielectric, and chi that is equal to 0 for vacuum. It is for vacuum, okay, it is chi that is equal to 0. Are you following? Okay, therefore, see, now I think you are able to understand. Okay, in the case of a single molecule, okay, in the case of single molecule, your P that is equal to, you can already, we have seen alpha epsilon naught E naught. Okay, epsilon naught inside. Why? In the single molecule, what are positive and negative charges? Okay, they are separated. Because of separation, here, what is that? There will be an induced dipole moment, and here inside only vacuum is there. Inside the atom only vacuum, but here that is why epsilon. Why I have taken epsilon here? What is there? See, once they are see here, once they are cancelling, what is there inside? Only everything is inside the medium. Therefore, you have to take what is that? P is directly proportional to E by here. P that is equal to epsilon, dielectric electric permittivity of the medium. Very important. It's not epsilon naught, it is epsilon. Okay. Oh, I hope you're following. Okay. Therefore, now therefore, let me give some equation. You know that E is equal to E naught minus here, na? We know that. Okay. We know now that the reduced value of the electric field E, okay, that is equal to E naught minus EP. Okay, but that what is EP? E naught minus EP. This E naught minus EP. Okay, and for that is nothing but E naught minus what is EP? E naught minus EP. EP is nothing but P by epsilon. Here, see, EP that is equal to P by epsilon. Are you following? That is nothing but E naught minus, what is P here? P is nothing but, what is P? This P is epsilon chi E. Epsilon chi E. Okay, divided by epsilon. Okay, P that is, it is P ma. Okay, P that is equal to epsilon chi E. Therefore, this will cancel. Therefore, you can get E that is equal to E naught minus, what is that? Chi E. E naught minus chi E. Are you following? Therefore, you can even have here, if you bring that, therefore E, if you take outside 1 plus chi, that is equal to E naught. Are you following? Therefore, 1 plus chi that is equal to E naught by E. E naught by E. What is E naught? External field. E is the reduced value of the electric field, and that is nothing but K. Are you following? Therefore, you can say that K that is equal to 1 plus chi. Very, very important result. Okay. Therefore, K that is equal to 1 plus chi. Okay, that gives you the, what is the relation between electric susceptibility and dielectric constant of the material. It is electric susceptibility of the material, dielectric medium. Okay, and therefore, and it is the dielectric constant. Therefore, how are they related? That is given by this equation. Hope you're following. Right. With this, we are going to apply the same concept in finding out. Next, very important, actually usually it comes for 3 marks, sometimes 5 marks coupled with the problem. Okay, everything is possible. Let me extend this one like that. Okay, now I have next topic is here. Very important question. See, capacitance. It's very bad. Capacitance of a parallel plate capacitor with a dielectric slab. With a dielectric slab. Okay. Now, very important question. Okay. Now, you know that consider a capacitor. Okay. Let me have capacitor like this. Okay. This is positive and this is negative. Therefore, here is positive charges are here, negative charges here. Okay. Okay. And the distance of separation is this parallel plate capacitor. Okay. Now what I am going to do is I am going to introduce a dielectric slab inside. And a dielectric slab is such that I am going to introduce a dielectric slab whose thickness is T. Whose thickness is T. Such that T thickness is less than the distance of separation, like that. Okay. Therefore, now you tell me, well, what will be different once I am introducing? Definitely there will be a polarization. Just now we have seen here, this side, negative charges will get accumulated. Negative is the center of, I think we have seen just now, dielectric polarization we have seen now. Okay, like that. Just like here, this case. Okay, therefore the same thing here. Now here immediately inside everything will cancel. Therefore the top surface is negative and bottom surface will be positive. But before that, there is a uniform electric field. Na? The uniform electric field I have to draw now, because it is kept in a external electric field. External electric field will be in this direction, correct? Positive to negative. It will be extended here like that. Inside the dielectric also field will be there. The applied field is E naught, that is in this direction. Okay, but inside the dielectric slab there will be electric field due to polarization. What is that electric field due to polarization? Will be positive to negative in this direction. Okay, therefore what will be the reduced value of the electric field? E, reduced value of the electric field, okay, will be, okay, your E naught minus EP. E naught minus EP. And what is the direction? It will be in this direction. Are you following? This is the reduced value of the electric field. Now, with this, whether you have understood the diagram? Okay. Therefore, now, what is the effective value of the electric field inside is E is equal to E naught minus EP, na? Okay. Outside the dielectric only field is E naught. But inside the dielectric it is E naught minus EP, right? Therefore, now, it is a parallel plate capacitor, na? Parallel plate capacitor, before introducing capacitance, okay, of parallel plate capacitor, okay, is given by before before introducing the slab. dielectric medium. That is given by, let it be C naught. Okay, that is equal to, what is a, it is nothing but, epsilon naught A by D, where A is the area of the plate, D is the distance of separation between this. Okay, right. Before introducing, only air is there inside, therefore it is epsilon naught A by D. Okay, but okay, now after introducing slab, let V be the potential difference between the plates. Okay, between the plates of the capacitor. Therefore, after introducing the dielectric, okay, after introducing the dielectrics, what happened? Dielectric medium, you can say dielectric medium, dielectric slab. Okay, the potential difference between the plates of capacitor V, that is equal to, now you tell me, very important, V is equal to, see, the electric field is not uniform. Outside the dielectric, electric field is E naught. Inside the dielectric, it is E. Correct? Therefore, both should be taken, V is equal to E into D. Na? But here, how to take here? It is E naught. Outside, it is E naught. E naught will be only for the space D minus T. Correct? Why? Total is D. T is the thickness of the dielectric. Therefore, outside the dielectric only the field is E naught. Therefore, it is outside dielectric. What is the distance here? It is D minus T. Correct? That is outside. But inside the dielectric, it is E only. Field is E. Okay? E into T. Okay? Therefore, the potential difference between the plates, it is here, it is divided to 2. Inside the dielectric, outside the dielectric. Inside the dielectric, electric field is E naught. Outside the dielectric, electric field is E naught. Therefore, E naught and D minus T, thickness. And inside the dielectric is E and thickness of the dielectric is T. Okay. Hope you are following. Therefore, your V is nothing but E naught into D minus T plus, you know that E by E naught, here E naught by E is equal to K na. Okay. Therefore, E can be written as E naught by K. Okay, so I want to express in terms of external field, applied field, E naught by K into T. What is K? K is the dielectric constant of the medium. Okay, of that slab that is introduced. Therefore, now you will be getting V that is equal to, if you take E naught out, okay, D minus T, okay, and plus T by K. Correct? D minus, plus T by K. Are you following? Right. But you know that is V equal to, what is E naught? E naught is equal to, in terms of surface charge density, sigma. If sigma is the surface charge density of the plates. Therefore, I can write this one, E is equal to sigma by epsilon naught. Okay, the into D minus T plus T by K. Okay, and that is nothing but sigma is Q by A. Sigma is Q by A, therefore Q by A epsilon naught into D minus T plus T by K. Hope you are following, children. Okay, so this is the potential difference. But what I want is the capacitance of the capacitor with the dielectric. Therefore, capacitance of the capacitor, okay, with the dielectric medium in between the plates is C. What is C? C is nothing but okay. What is C? C is nothing but Q by V. Q by V. Okay, that is Q. Already V is there now. V we have calculated by, okay, what is V? Q by A epsilon naught. Okay, V in the place of V into D minus T plus T by K. Okay, therefore Q will get cancelled. Therefore, your C, that is equal to C naught is the external field. By C naught is without medium. Now C is the with capacitance with medium. Okay, so C, that is equal to epsilon naught will go up. Therefore, you can say epsilon naught A divided by D. If you take D minus T plus T by K na. Okay, and that is nothing but I want to bring in the C, that is equal to epsilon naught A divided by D minus, you take T outside. If you take T outside, you will be getting 1 minus 1 by K. Correct? 1 minus 1 by K. So, this is the expression for what? The capacitance of the parallel plate capacitor with what? The dielectric medium inside. Okay. Therefore, here from this I think it is understood that epsilon naught A by D means C naught. But here epsilon naught A by D minus something. Denominator here is decreasing. Therefore, you can say that C is definitely more than C naught. Correct? Why? C naught is epsilon naught A by D. But here epsilon naught A by D minus something. Therefore, denominator here is decreasing. Denominator decreasing means definitely capacitance will be more. Therefore, you can say that introduction of dielectric slab in between the plates of the capacitor will increase its capacitance. Okay, it will increase its capacitance. Are you following? Now shall we go for special cases? Only special cases. Number 1. When T, that is equal to D. What do you mean by T is equal to D? Dielectric is fully filling the space between the plates. Okay, therefore, okay, it is here T is less than, so far we have done here is T is less than D. Correct? But here T is equal to D means what will happen? In that case, you tell me what is the formula? C, that is equal to epsilon naught A by, okay, D minus okay, D plus D by K. This equation becomes like this. Okay, this will go. Therefore, you will be getting K epsilon naught A by D. Okay, therefore, capacitance C, that is equal to K into C naught na? K into C naught. Okay, are you following? So, that is correct only na? K into C naught. If a dielectric is fully filled means, what is it? It is K into C naught. The same thing we are getting. Here it is not fully filled. Some thickness, only some space is filled. So, this is the expression. If it is fully filled, it is like, okay, right. This is a special case. 1, 2. Second case, simple. Second case is when, just one, when you can say T is equal to D by 2. T is equal to D by 2. Therefore, I think T is equal to D by 2. What will happen? Tell me. What is your C is equal to epsilon naught A divided by D minus, okay, T is equal to D by 2. Therefore, D by 2, okay, minus, minus not, plus, okay, what is that? D by 2K. Correct? Therefore, you will be getting here epsilon naught A. Hope you are following. minus it is d by 2 d by 2k, right? Therefore it is epsilon naught a, okay, by a to d by 2, d minus d by 2 plus d by 2k, d by 2k. Are you following? Therefore if you solve this, you will be getting 2 epsilon sorry, if you solve this one, you will be getting 2k this d inside, therefore you will be getting d by 2 epsilon naught a by d. Therefore you will be getting this one as 2, okay, epsilon a by d will be c naught na, therefore 2k c naught divided by 1 plus k. Take LCM, that is it, okay, 1 plus k. I think you take LCM for that, you will be getting this. Okay, therefore this is C, that is equal to 2k C naught. C naught is epsilon naught A by D. Okay, therefore this will be the case. So this is when it is T is equal D by 2. Are you following? 2k C naught plus 1 divided by 1 plus k. So this is the value. Okay, hope you have understood. Okay, that's it for today.